Hello, everyone. I think we can start. Good afternoon, everyone, and welcome. My name is Wanju Yuan. I'm the part of the program teams for the SPE category section, Young Professionals. And I'd like to thank you to join us today for this webinar to hear how Eavor is changing the face of energy with the world's first zero emissions load following resource. And thank you to our sponsors, Chevron, Hexagon, Geologic System, and Oventive for their continued support for our technical programs. And before introducing our speakers, I would like to let everyone know we are currently live streaming this webinar via our SPE Calgary Facebook account, as well we are recording this session, which will be available via our SPE Calgary YouTube account. I'd like to highlight some recent SPEYP events. We will have a webinar on November 26 regarding forecast the electricity prices in Alberta by using machine learning approach. It is an event under our SPEYP's data science mentorship program. So if you have interest in machine learning or just curious about the future electricity price, feel free to join us. You could find more information from our website or SPE newsletter. We will continue the ZELFR challenge of this month. It's an online monthly fitness challenge through the ZELFR app. There are usually monthly meetup in person and prizes awarded to the challenge leaders. So feel free to download the app and search the SPE Young Professional Calgary Club and join the group of the monthly fitness challenges. So welcome to download the app and join our team. Last week, we'll have our SPE Young Professionals social holiday mixer. More details will be posted in next month, so stay tuned for our upcoming holiday mixer in December. It's time to introduce our speaker today. Our speaker is Bailey Schwartz. Bailey is a professional and engineer with a decade of hands-on engineering experience that focus on data analytics and process optimization. Bailey has a passion for innovation, actively seeking opportunities to trial the new technologies and push boundaries. Since joining the Eavor team, Bailey managed the construction, commissioning, and operation of the Eavor-Lite Demonstration Facility, and was the project manager of their Germany first commercial project, and is now involved as the director of North American Eavor-Loop projects. Following the presentation, we will have a Q&A session, so you can leave your questions or comments in the Q&A window below, and I will ask those questions to Bailey for you. Okay, please join me to welcome Bailey Schwartz.
Thanks, Wanju, and thanks to the SPE for inviting me to speak to you today. I am just going to share my screen here. So, Wanju's already provided a bit of background on me, but my name is Bailey Schwartz. I'm the director of North America projects for Eavor Technologies, and my background is in chemical engineering. I spent the first 10 years of my career at Synovus, doing operations engineering, production engineering, and then a few years ago pivoted to join a startup company, Eavor. We were 8 employees at the time. Since then, we've grown to about 40 worldwide. And so what we've done is we've really developed this novel form of geothermal energy that's broadly scalable. And our goal is to enable a geothermal everywhere type of solution. Today I'll go through what that technology is, more of a technical perspective of what the system design approach is. I'll give you an update on our pilot project, which we've now been operating for 2 years. And then I'll look forward into commercialization, how we're planning to take this to market. So to kick things off, an overview of the technology, and I've got the acronym ZELFR on here. So ZELFR is a Zero-Emitting Load-Following resource. It's basically this unicorn of renewable energy that can actually provide energy on demand when it's required. So when you look at how that actually fits into the typical characteristics that we look for in energy sources. Right here, I'm showing different attributes. So baseload, clean, and scalable. In scalable and clean, when you've got all the renewables that typically get a lot of advertising, wind, solar, and storage. They're not baseload though, they're intermittent. So if the sun's not shining, the wind's not blowing, or storage, really you're kind of limited to a 4-hour discharging capacity. You can't provide power for parts of the day when you have those conditions aren't present. You've got things like baseload, which probably many people here are familiar with: oil and gas, coal, biofuel, nuclear, hydro. But when you're looking at energy transition and these global, emissions reductions targets, we're looking at ways that we can either do carbon capture and make those greener, lower emitting sources, and then clean. So where the Eavor-Loop fits is basically at the transect of all of these different attributes. So it's scalable, it's clean, and it's baseload. And it's also dispatchable. So you can basically kind of charge up your system and then discharge it when the energy is most required, which I'll touch on in more detail as well. So really looking at how this compares to traditional geothermal and why traditional geothermal isn't scalable. To date, I think geothermal energy accounts for less than 2% of the global energy production, even though it's an abundant resource. Heat below your feet, the deeper you drill, the more heat you're going to get. So why don't you see more geothermal out there? Really what's limiting it is that it's an open system. So you have, in a traditional geothermal system, an injection well and a production well, and you're relying on the natural permeability or induced permeability through EGS or fracking to actually allow that fluid to flow through the reservoir, pick up the heat, and then be produced out. You're producing out a brine on the production well side. What we're doing in Eavor-Loop is we're actually building a closed system. So we drill our 2 wells, our inlet and outlet well here. The blue would be your inlet well, so the cold water is injected. And what we're doing is we're creating essentially a big radiator subsurface. So we're drilling multilateral wells that intersect at the toes and forming these loops that it's a big heat exchanger. So you're relying on conductive heat transfer. You're not doing any exchange of brine with the reservoir. You're basically sucking heat out of the rock, producing it to surface, and then either extracting it for a heat application or converting it to power on surface. So the benefits of this is that you don't need to locate that rare permeable aquifer, and it's one of the reasons why there's so much exploration risk with traditional geothermal, similar to oil and gas exploration, and why you can't term traditional geothermal as a really scalable solution. One of the other big benefits of our system is because it's fully closed loop, you have this natural driving force, this thermosiphon that's generated because you've got a volume of cold, higher density fluid on your inlet vertical well relative to your heated fluid on your outlet well. And that density difference naturally propagates the flow through the system and creates that pressure required for the circulation. So you don't need a pump while you're operating, versus a traditional geothermal traditionally requires an electric pump to circulate that brine, which can be 20 to 30% of the gross power generated, just a parasitic load to run that pump. So the overall efficiency of the system is drastically improved. I mentioned here we have no fracking, no induced seismicity, which can be concerned with traditional geothermal, or more specifically with enhanced geothermal systems where you're fracking to promote that flow through the reservoir. Because you're not producing any of the brine, there's no GHGs or CO2 that can be produced with a traditional geothermal brine, and really minimal continual water use. Once you fill the system, it's basically just an isolated system, and that water, that initial volume will continue to cycle. Versus for traditional geothermal, typically you need to do some makeup water for pressure and reservoir maintenance and management. And water is becoming a very increasingly valuable resource. So a lot of projects that you look at, that can be a big limiting factor as well. The OpEx is really low. You don't have the costs associated with the parasitic pumps, scaling, or corrosion that you'd see on a traditional geothermal plant. And the thermal output risk is really low as well. So once you've kind of defined what the geothermal gradient is, so how much that temperature increases per kilometer of depth that you are drilling, and you have an idea of the thermal conductivity of the rock, which you can get from a mineralogical analysis of that formation, really that thermal output risk is just, it's a physics problem. You're looking at conductive heat transfer through a rock into a fluid flowing through a pipe. So once you calculate that out, there's a very narrow range of certainty on what that thermal output will be over a very, very long project lifetime. So we can operate with no degradation of our output over a 30-year project life, based on kind of picking a year 5 output to design to. And then we can keep operating for 100+ years, just with a marginal decline over that extended lifespan of the project. The cycle time, 2 years. So like I said, you can understand what that output is going to be very early on. So you can actually do a lot of work in parallel in terms of drilling, designing a power plant, and constructing the whole system. Versus traditional geothermal, there's an exploration phase, a testing phase, then a design phase, and then you're finally into execution. So it's typically a 5 to 10 year cycle time. And most critically, and where that ZELFR acronym comes in, is that it's got this baseload and dispatchable characteristic. I'm not going to get into each of the key advantages because we've got a really great website. So if you guys are interested, go on there. Basically, we've spent a lot of time over the last 2 to 3 years designing and really refining the technology. So we've got a lot of IP in terms of how we actually drill and construct these enhanced fluids for what we're flowing through the systems, work on how we can minimize the surface disturbance and footprint. So yeah, really trying to make sure that the technology product that we're offering is the most optimized, most competitive product on the market. So looking at the footprint, so I think this is just a good comparison to see for the same annualized output when we're talking about solar and wind, which a lot of people are kind of focusing on for this energy transition, how much space that actually requires and why this can be a really great distributed solution that you can locate close to cities, in communities. It's a distributed energy resource. So for the same output, you can see 300 hectares for wind, about 1/10 of that, so 35 would be an equivalent output for solar. And then that's about 1 hectare required for an Eavor-Loop for that same output. So the surface footprint's really small. For us, it's that subsurface footprint as you're building out that radiator section that is where all of that, that surface area is really developed. So just another point on the positive environmental impact, one of the questions we get a lot is, okay, so when you're producing, you're not emitting, obviously you're not generating any emissions, but if you consider the whole life cycle, like the emissions that are generated when you're spending 1 year or 2 years drilling out big projects, and then any of the consumables that you're using for facilities, you know, casing of your wells, things like that, how do you actually compete, and are you offsetting those emissions required to construct as you go through the life of the project? So we worked with a company called Boundless Impact, and they, Boundless Impact Research and Analytics, and they did a full life cycle assessment of Eavor, at the Eavor-Loop electricity, and then compared it to, you know, offshore wind, nuclear, solar, and then hydrocarbons, natural gas, oil, coal, and lignite. And you can see that we're basically on par with wind and nuclear, and about 4 times better than solar when you look at that full life cycle of the emissions associated with building and operating that project. So definitely, you know, really positive environmental characteristics for the technology. And I think the most interesting and compelling when we're looking at things like the robustness of the transmission systems and grids is a lot of problems that are happening in places that have a high penetration of renewables like solar and wind, is that there's these rolling brownouts or lack of stability in the grid, because you basically have these peak periods of the day when you've got a lot of production followed by pretty rapid declines as the sun goes down or if wind stops. And we don't really have a good solution right now to backfill that capacity outside of having natural gas turbines and solutions like that can respond on demand until you add the Eavor-Loop into the mix. So basically what we can do is we can turn down the system or kind of slow the circulation rate and store that heat subsurface. And then when needed, you can speed it up and produce it and actually produce over kind of a baseline nameplate capacity and be able to dispatch that energy without degrading the total output over the life of the project. So you're basically just storing and discharging with a really high efficiency. So if you look at, how this technology could complement a solar plant, for example, you can see in the chart here on the right-hand side, if solar is out of service during the nighttime hours and then kind of picks up around the morning and runs for most of the day, the Eavor-Loop, rather than operating as just a baseload 10 megawatts of output, could actually ramp back, peak when people are waking up and the solar energy is not available. And then you could ramp it back down during the main part of the day when there's ample electricity from the solar facility. And then again, at the end of the day, when the sun's setting, you can ramp back up and meet the evening need for that market. So, so looking at ways that we can partner with existing technologies to increase the robustness and the stability of the overall grid system as well. So we've done a lot of work looking at that. That's really interesting. So just getting into the system design now, what we do is we basically have a thermodynamic model that we've built out that lets us calculate how much heat, how much thermal energy we're going to be extracting from our Eavor-Loop subsurface. And then we couple that with a surface model of whether or not we're selling heat or selling power, what the power plant looks like. And that's really how we're looking at the overall output of the plant itself. And then that feeds downstream into economic models. So we get a full thermoeconomic view of what these projects will look like. In terms of the thermodynamic modeling, we've done a lot of work making sure that the modeling that we are using is valid. So we've built a series of 3 in-house models of increasing complexity. You can see here the most basics, the analytical equation, works kind of for the base steady state assumptions, but doesn't give you a lot of the additional detail that you need for the system design. Then we move into a 1D steady state model. And so that gives a lot more. This is really kind of the base model that we use for all of our project scoping. And then we've also validated with a 3D model, 3D transient model. So this lets you do time variant inland conditions, test out that dispatchability feature of the Eavor-Loop as well. So we built these models, we've run them all against each other to make sure that we're getting really good consistent alignment between the results. And then we've also had our studies or our modeling validated by numerous third parties. So, both giving them kind of independent assumptions and letting them build their own comparable geometry loops and coming up with the same answers, or going through our methodology and kind of vetting our methodology as well. So we've worked with NREL in the US, TNO, that's a research organization based in the Netherlands. We've done a lot of work with academic institutions. UT at Austin and the University of Toronto have all replicated our work with good agreement. And I think there's recently been a paper published by the Canadian Geological Survey as well, that's available to the public online. So yeah, I think we've got at this point a lot of confidence in the modeling, and we also have some results that I'll share with you shortly from our pilot project showing the results in the modeling compared to actuals. So I'm not going to talk a lot about this. This is just kind of so you can picture how we approach the modeling. This is showing a simplified 2 lateral Eavor-Loop. And zooming in onto a single box here, in the orange, this is the fluid flowing through our lateral wellbore. And then the gray is the rock surrounding the wellbore. And what we do is we discretize. So we split that problem into a whole bunch of little slices of rock and of fluid flowing. And then we look at, conservation of momentum, conservation of energy, as you've got that fluid flowing through the wellbore, and as you've got heat that's basically being transferred in every direction from the rock to the fluid, from hotter rock to colder rock. So really kind of a complex or a discretized model that it solves in increments as you step your way through the full system. So what you do is you kind of input your inlet well parameters, so the pressure, temperature, and flow that you're entering the loop, and it will work its way through this whole subsurface system and calculate out your outlet conditions, so the temperature and the pressure that you're now producing at. And it will kind of output a chart that looks like this on the left-hand side. So this is assuming I've got a constant inlet temperature and a constant flow rate. What this is going to do is it's going to tell me that my outlet temperature is going to start higher and then decline more significantly in the kind of the first 5 to 10 years, and then a pretty stable and minimal decline beyond that point. And my heat output, same thing. You can see it kind of declines and then tends to stabilize as you get to year 10 and beyond, which is what you would expect to see, is that radius where you're cooling the rock around immediately around the wellbore cools, you're going to have less heat that's transferring out. So as I mentioned, what we do is we will pick a design point that will give us a representative flat output for a 30-year project life. And so we would say here, it might be, a year 5 or year 7 design point that would kind of give you that annualized output over time. But we have flexibility for how we would operate it. So you could choose to operate at that maximum thermal output and just have your energy decline over the 30-year life. The other really critical tool that our modeling gives us is the ability to understand how that thermally affected radius will grow over time and ensure that we're spacing the multilateral wellbores far enough apart that we mitigate any of that interference in the early periods or within that 30-year project life. So we make sure that the modeling is valid because we're not seeing that thermal interference between the lateral wellbores. So the other output from our model is showing what's happening on the rock temperature. So this now is looking, assuming on the left-hand side here, this would be my inlet well, my inlet vertical well, and this would be the heel of that well. Then that cold water flows and is gradually heated up along the lateral wellbore, and then is produced up the outlet well. And this is just for simplicity showing one lateral, but we would have 12 of these that would all be spread out and constructed beside each other in parallel. And so what you're seeing is after 1 year, you're basically getting a pretty minimal thermally affected radius, so thermally affected zone around your lateral wellbore. The scale's a little bit hard to see, but right about here is 5 meters, and the whole scale goes up to 50 meters. So 50 meters from your lateral well. So after a year, you're maybe getting 2 to 5 meters of affected zone. After 10 years, this is growing to, maybe 10 meters, 30 years. And you can see even after 100 years, like you're still reaching basically virgin rock temperature at that 50 meter rock, at that 50 meter mark. So still an ample amount of heat to be extracted for very long. These are very long lived acids that can produce electricity for many years beyond the 30-year project life that we designed for. In terms of the process itself, so the Eavor-Loop is shown here. We have our cold water going in the inlet well, heating up through our subsurface radiator kind of portion, and then produced out. And on surface, it's pretty straightforward. We just exchange that heat with another closed loop. So this would either be directly to a district heating network that would then distribute that heated water to buildings or to campuses or whatever that end use might be. Or in electricity applications, this would be a closed loop of an organic Rankine cycle type of heat engine. So basically, you'd have a lower boiling point organic fluid. As it's heated up, it's going to vaporize. So now you've got a high pressure, high temp gas. You're dropping that across the turbine and generating your electricity. And then you have an aerial cooler that's going to come and condense that low pressure gas or vapor now back to a liquid and pump it back through the cycle. So quite straightforward. These are commercial off-the-shelf products that we would just be purchasing from a supplier on a turnkey basis. So I've got an example from Turboden in here, just showing that they're operating in 50 countries, 400 plus plants, really, really high average availability of 98%. There's Ormat and Exergy, those are kind of the top 3 market leaders in this space, but there's lots of options for these off-the-shelf type of heat engines that we can partner our technology with to do that final step and convert the heat to electricity. And then on the right-hand side, this is just a power plant in Orsi in New Mexico that I'm showing for reference. So this would be your aerial cooler portion, your evaporator and preheaters, and then basically that's, your turbine generator over here, and that's the bulk of the surface footprint. So most of the footprint's taken up by the aerial cooling system. And as I mentioned, there's different, the way that we can operate these Eavor-Loops is really, really flexible. So we can change our inlet conditions, our circulation rate, our reinjection temperatures, and basically control for the properties that we're producing out on the back end. So in this case, this would be operating at a maximum thermal output. So the heat output in yellow, same case I showed before, where our inlet conditions are constant, and this would decline over time. Alternatively, you can set a flat heat output and you can just increase your circulation rate over time as well. So what this enables us to do is to partner with these organic Rankine cycle manufacturers and do a lot of iteration through the design phase to make sure that we're designing the most optimized integrated system. So between the Eavor-Loop on subsurface and the facility on surface, how we're really making sure that we're getting the maximum amount of power, because we do have some levers that we can pull to tailor those produced fluid conditions to what the ORC will what will get us the highest efficiency out of the organic Rankine cycle. Okay, so that's kind of an overview of the technology and how we approach the design. So Eavor-Lite, this is a project that we constructed back in 2019 in Rocky Mountain House, so just kind of by Red Deer, Alberta. What this was really kind of a scaled down version of an Eavor-Loop. We were trying to pick the most cost-effective way that we could prove out the three kind of key questions that kept coming up from investors. Can you actually do this? So number one was, can we actually drill and intersect these two wellbores kilometers below the surface? Number two, can we actually seal and pressure test the Eavor-Loops? And I should have mentioned earlier, we don't actually case the lateral sections. We actually seal that with a rock pipe completion system. So it's a chemical sealant that we've developed in-house that chemically seals that wellbore. And then number three was the thermodynamics. We've done all this modeling. Do the actual results line up with the predictive results that we're getting from our modeling? So what we did is we built a scaled down version of the Eavor-Loop. We have an inlet well and outlet well at about 2.4 kilometers total vertical depth. And then the laterals themselves are 2 kilometer distance or length. So really scaled down version. If you think about a commercial project, this would typically be 3 to 5 kilometer depth and a 6,000 meter lateral, 5 to 6,000 meter lateral section. And then 12 laterals rather than just 2 here. So we picked a scaled down version so that we could cost effectively, again, prove these 3 key objectives. On surface, we just given the partner that we were working with and the accessibility on surface, we ended up doing a pipeline tieback between the 2 locations. So this is something that you wouldn't typically see on a commercial project. We'd have the 2 wells co-located, which I'll speak to a little bit at the end of the presentation. And then in terms of what we were doing with the heat here, because we're not close to a grid, there's not really a heat user offtake at this location. We've just got an aerial cooler that's extracting the heat from the water to show that the thermosiphon will work, but we're not using the heat for anything. It's just a simulated heat user that allows us to establish that delta T for the thermosiphon to be tested. So high level timeline, we started design on this back in Q1, Q2 2019. Q3 we drilled, Q4 we built the surface facilities, and then starting in December we commissioned and we have begun operating the facility. On the left hand side here you can see the 2 drilling rigs, that little speck in the background. So that they are 2.5 kilometers apart, but you could stand on the one rig and see the second one in the distance. This shows an as-drilled profile for that intersection point, excuse me. And then the team that actually was on the rigs responsible for that first intersection. So this intersection technology, it's active magnetic ranging, something that's used in industry typically for relief wells and well intervention, or for SAGD for ranging of well pairs. We actually used it, flipped it on its head and used it for the opposite purpose of intentionally intersecting well bores, rather than kind of the avoidance piece. And then this is just a picture of our fully commissioned facility. So pretty straightforward surface infrastructure. We've got a storage tank. This building houses our production wellhead and some metering. And then this building holds our control kind of monitoring panel, metering, and then a little startup pump that we ran for 4 hours to get the system actually running and establish that temperature difference. And then the aerial cooler is just on the back side of this building here. In terms of proving that we could drill and we could actually complete the system, we successfully completed 2 intersections for the 2 laterals that I showed. The first one was nearly a direct hit. We had about 84% coverage. So you can see on the left here, the green's the well bore that we were approaching, and then the blue is as we were drilling in and basically got that, that almost perfect intersection. The second one, we learned a lot more as there was some interference because we now connected one of the lateral well bores. So great learnings, I guess, in terms of how you would then apply that to scaling up for 12 intersections for a commercial project. And basically, it just took a little bit more time to steer and intersect into the second well bore, but we were able to successfully do that and confirm a full mechanical intersection on both well bores, or on both lateral legs. So in terms of our sealing, this is showing our rock pipe. This is some plug testing we did in the lab, some sorted core with plug flow testing. So we're flowing the rock pipe through that core. So what it does is it basically permeates into the near wellbore and then sets up, and that's what's preventing any fluid from your system leaving or from the reservoir coming into the system. In addition, we're operating basically in balance with the reservoir, so making sure that we're not creating a huge driving force for fluid transfer to occur. So what this trend is showing is, since we started up at the beginning of December 2019, we're monitoring the overall volume of the system, and we're trying to track whether or not we are seeing any of our Eavor-Loop fluid being lost over time. And so when we initially started up, we were seeing, and I've got this as a percent of system volume, so this is around like 0.6%. We'd set kind of an internal target for criteria here. And what you're seeing is that there is a very, very minimal amount of leak off. So right now we're stabilized to less than 0.1% of the total subsurface system volume. But we're continuing to see this downward trend over time. And again, because now what we're using this Eavor-Lite facility for is it's an R&D test site for us. So if there's things that we're trying to understand better about the system or that we want to test out, we can go and use this as a test to get a pilot scale test completed. So we've been looking at, different ways that we can supplement the sealant, and just in general how this trends over time, because naturally in the fluid, the sealant is kind of circulating in perpetuity. So if there are any leak points, by its nature, it would leak off and then self-seal at those locations. So we'd expect to see this continuing to trend down over time. But this is an area that we're continuing to do more R&D on as well. And then in terms of the thermodynamic modeling, how's the performance relative to what we had predicted? So what's shown here in gray is the circulation rate. So, initially we were trying to operate things fairly steady state, and then we were running a few trials where we were changing the flow rates around. In orange, the orange line up top here is the predicted output, and then the little circles are the measured output. So since we've started up, and this is 60 months of data, the mean absolute error that we've seen from our modeling is only 0.37%. So really, really good agreement, as expected, because it is a conductive heat transfer problem and not a lot of complexity once the models are built and structured. But really, really good agreement with the predicted results. And so this extrapolates to future commercial projects when you're looking at what assumptions have gone into building that model, that we can estimate that output within a very, very narrow range. And there's a lot of certainty on what that performance will be over very long time spans. And I guess for the dispatchability piece as well, you can see like areas here where we've actually stopped flow for a period of time. This is testing the recharge. So are we properly accounting for heat that once you stop circulation, your wellbore is going to heat back up? And so you can see that that actually is the case, and it's being accounted for properly, that when you start back up, you see a bit of a spike in temperature, and then it starts to trend back with that decline that you would expect. The other interesting thing we did at Eavor-Lite is we placed a 6-point thermocouple string in the outlet well. So what we can do is we can actually measure the temperature profile at 6 discrete points as it's being produced at the vertical outlet well. And you can see from the trends on the left-hand side here as well at each location, we're seeing really good agreement throughout as well. So that just means, again, more confidence that we understand the physics and what's happening as that fluid's being flowing through the full system. So that's kind of where we're at. So we've had this pilot project now being operational for 2 years. Really the focus of the last year has been to look at commercializing this technology. So where kind of the near-term focus areas for us, it's areas where there's good, because we are a new technology, we're kind of at that peak of the cost curve. So solar a decade ago, when solar panels weren't so cheap, you can think of the exact same thing here. So we're kind of at the highest point of the cost curve. We're looking at markets that could support first commercialization. There's places like Germany where they've got geothermal feed-in tariffs that support a significantly higher electricity price for a 20-year duration, because the policy there is trying to promote more geothermal activity. So those are some of the early markets that we're looking at. In Germany in particular, we've got now a German office set up. We're looking at a first commercial project that we're developing just south of Bavaria in Germany, and then a whole bunch of other prospects that are coming along the front end of the project development pipeline as well. And then focusing on how we're really going to come down that cost curve through basically manufacturing. This is similar to how drilling costs have improved in some of the big, like the shale revolution, as you see drilling costs drop to 60% of what they had initially been over a decade of drilling that same type of geology. We're expecting that you'll see those exact same cost curves appear as Eavor-Loop start getting built and rolled out globally. And so so basically as a company, we've now got this pilot. We're focusing on commercialization. We've raised 100 million Canadian to date. Most recently, that included conventional energy super majors. So people like BP and Chevron that are strategic partners for us as well, because they have the technical and operational experience to help us now commercialize the technology. So looking forward to 2022, that's where the continued focus and emphasis is going to be on how we build these first commercial projects. We're also looking at the next iteration of the technology. So constantly trying to figure out how we can improve the system to increase efficiency, to drive down costs, to make it more competitive globally. So we're looking at doing some trials on some of those new technology elements next year as well. So just kind of a high level of what that looks like. This is showing the commercial configurations. This basically, when I mentioned before, the Eavor-Lite had 2 separate surface locations. For any of our commercial projects, that would actually be kind of cut in half and flipped in on itself. And both of your inlet and outlet vertical wells would be drilled from the same location. And then your laterals intersected the toes in a bit more of a hockey shape type of configuration here. So a little bit better from an execution point of view, because when you're doing your lateral drilling and you're doing that ranging, you've actually got clearer line of sight for how the trajectories are lining up and how you need to be positioning for the intersections to occur. So just looking at kind of the technology roadmap here, Eavor-Lite, we've executed. Eavor-Loop 1.0 is essentially this design, but you're targeting sedimentary zones here. And so the laterals kind of extend it at a 90-degree angle and are chasing that sedimentary zone. And the next progression of the technology for us and kind of moving into that global, fully scalable solution is actually accessing the igneous basement rock. And so what we would do is we'd drop the the lateral legs down to a, more of a pitchfork type design. So they're propagating down instead of at a 90-degree angle. And what this allows is it basically boosts the thermal output per installation, because now you're accessing a higher average rock temperature for the whole placement of that radiator zone. So, a lot of considerations that we look at as we're kind of scoping out and building out our pipeline and our commercialization strategy, but really right now focusing on 1.0 type projects in markets that support them, and then moving on to demonstration of that 2.0 technology. So I think I'm pretty close to being on time, but there is, I've included on here, and this is on our website as well, lots of really cool things on there. There's a virtual tour that kind of walks you through the whole demonstration project, a video that explains the technology in more concise detail than I did today, and then a whole bunch of articles. We're getting a lot of interest just because there's so much emphasis on ESG kind of investment, energy transition, renewables, and we truly are that only resource that can be a ZELFR that can contribute to the energy stack in that way right now. So so that's basically everything I'd prepared, and I'll hand it back to Wenju for Q&A.
Okay, thank you, Bailey. That's very good presentation. A lot of information behind on the slides. Okay, I will ask you the question from the Q&A window. The first question is, how are you defining your 2 years cycle time from the final investment decision or from the start of the drilling?
So it would be from, I'd say 18 months from final investment decision. And drilling times will play into that. But another benefit of what we can do is, because we're drilling, maybe 4 or 6 Eavor-Loops in a single project and trying to scale up that output accordingly, the lead time on the power generation facilities is typically 18 months. So that would be you'd be teed up to sign that contract upon FID, get the ball rolling there. And then as soon as that power plant's constructed, you can be drilling the Eavor-Loops in parallel. So the first Eavor-Loop can be completed, tied into the power plant, and actually have a cash flow generating asset while you skid down and continue to drill loops 2, 3, and beyond. So we're thinking about ways that we can make that cycle time as short as possible. And it's a flexibility and execution that we have the privilege of playing with, more so than technologies where you have to build the whole thing out before you can start actually operating.
Okay, thanks. Next question is, what is the electrical output from the slide 3? It's mainly regarding the energy conversion efficiency, because your results are based on the heat production. So how about the electricity part?
Yeah, so it depends. Yeah, it depends on the project specific kind of inputs. That thermal gradient and the rock conductivity are kind of the 2 key things that drive the thermal energy that can be produced. On surface, it's working with those ORC vendors to figure out how we optimize and increase that conversion efficiency. So I'd say for the kind of the standard 1.0 design right now, we're between 2 and 4 megawatts, depending on the thermal gradient of electrical output. As you move into the 2.0 type of design, you can actually boost that up to like 4 to 10 megawatts of electricity per Eavor-Loop.
Okay, the next question is, what is the working fluid, the pure water?
So the starting working fluid is basically water. But there is a lot of work mainly because it works, it's got good heat capacity, and because it's an easy commodity for regulators to understand as we're moving through and doing rock pipe completion, that they're just less comfortable and haven't permitted that type of systems before. But we are doing a lot of work on enhanced fluid as well, and looking at ways that we can improve the efficiencies of the systems by using some alternative fluids. Okay,
so why not cool the steam with the Eavor-Loop fluid itself instead of the area coolers to preserve the energy withdrawn from the reservoir?
So that's a good question. I'd say there's lots of different heat integration options that you can look at. It's basically kind of I think an efficiency, so when you're looking at the overall heat profiles of the Eavor-Loop and the ORC system, it's not always necessarily a better way to cool that organic Rankine fluid with the Eavor-Loop fluid. And then you're looking at, different types of cooling. So what we're trying to do is a bit of a more modularized, repeatable type of design that we can then go and deploy on any project. And it helps to drive the cost down. We're not re-engineering a whole bunch of different stuff every time. So I'd say it's not something that you can't do. It's just something that would have to be evaluated on a project by project basis. And the standard design from the ORC vendors right now would be either aerial cooling, or if there is source water nearby, if there's, ocean water or lake or stream that you have access to, that could be an option as well.
Great. Why not use the water coolers, especially in summer months or lower latitudes?
So yes, they definitely help with the efficiencies because you're not pinched by ambient temps. Typically, the only reason that you wouldn't use water coolers is because there's no cold source water nearby. So in the project locations that you do have access to that would likely be the way that you go.
Okay. The next question is, how do you optimize or manage the hydraulic effects, pump power, and the frictional pressure losses given the high flow rates, because your flow rates mentioned is from 20 to 100 liters per second?
Yeah, so that's a really good question. That's part of the overall system design and optimization. Is you've basically got pressure, driving pressure that you're generating through that thermosiphon differential, and then you're going to have frictional losses as you flow through the system. And so what we need to do is we need to basically kind of tweak and adjust that flow rate to make sure that we're producing the optimal amount of thermal output, but staying within that thermosiphon available pressure and making sure that we'll still be able to operate. I mean, there's also cases you can look at where maybe it would make sense to have a circulation pump installed because you could boost your output that much more. Typically, though, especially as you look at, as we progress into the 2.0 type technology, where you're actually angling your subsurface loops downwards, in those cases, you have the thermosiphon generated pressure is so substantial that there's a lot of room to play with there.
Okay, great. Was there an efficiency impact as a result of the ghost hole after missing the initial target intersection?
Not really. It's more of a CapEx issue. So it's that 80 meters that you drilled that you're not getting benefit for. But in terms of the total connected lateral that you're seeing flow through, it's going to be the same length. So no efficiency loss as a result of that. Okay.
Does the ramping output from the Eavor-Loop have any impacts on the system's efficiency, performance, reliability?
So the way that the surface facilities would need to be designed would be for the peak power that you're going to be producing. So, if your baseline capacity is 10 megawatts, but you're going to be peaking at 20 or 25, there's more CapEx required to build the plant up to that 25 megawatts. That's work that's done with the ORC vendor to understand any efficiency impacts. There's lots of ways that you can look at how I would actually design that too, by having, potentially turbines in parallel, or systems in parallel, so that you maximize that overall efficiency again. But in terms of reliability and any issues like that of cycling, nothing that other than maybe a bit more PM on certain components in the system. There are biomass installations that operate this way typically. Like I've seen some trends from our ORC vendors as we've been talking through the implications of operating this way, that don't suggest that you're going to see, significant decline in efficiency or increase in OpEx associated with that type of operation.
Okay, great. The next question is, will Bavaria wells be drilled in a hard rock or in the basal sedimentary rocks above the basement? Do you anticipate any additional well engineering challenges in that area?
So the target zone in Bavaria is the sedimentary package. with future expansion potential to go into the basement rock at a future date. If we're building out, we're approaching this the same way that oil and gas would, like a resource plays, where you kind of prove up your resource, and then there's lots of capacity to kind of continue building out more well pairs, more Eavor-Loops. So currently planned for the sedimentary package. I mean, I probably shouldn't speak to all the drilling stuff. We've got Mark Hodders, our manager of drilling engineering, that is much better equipped to speak to any of those types of questions. But in general, we're working through the detailed well design, and there's the standard like anti-collision type of considerations. There's a lot of detail and thought that's going into how the intersections will take place, how we're doing the junctions, the spreading sections, but all of it's kind of commercial off-the-shelf technology. So it's now just kind of fitting all those pieces of technology together and making sure we have a comprehensive drilling program in place.
Okay, so it's in a sedimentary. So how far above the basement rocks will the loops be located in the Bavaria, and what is expected reservoir temperature?
So in this case, it's a pretty average geothermal gradient here, about 32 degrees per kilometer. So similar to actually what we drilled from a geothermal gradient in Rocky Mountain House. There we only went to 2.5 kilometers. Here we're looking at around 4 to 4.5 kilometers as our target depth. And then it's quite a thick sedimentary package here. So I think the basement rock, again, I need to confirm this with the geologist, but I think it starts like 5 to 6 kilometers below surface.
Okay, the next question is about the drilling. How does the casing or cement differ from the conventional drilling? Is the entire casing length insulated? So
the casing and cementing on the verticals would be the same practices that you would see on an oil and gas well or a geothermal well. You're going to be designing to the same for the same geohazard avoidance. Basically, anything below that ICP is going to be open hole cased with our rock pipes. That's where you might see like the higher temperature, extremely high temperatures, things like that. So that's not within the cased zone. So that's why we can use standard practice for how we're casing and cementing. Things like insulated tubing are things that we look at on each project to see if the benefits of having that it's an economical decision for the project. So how much incremental thermal output you'll get by producing to the surface with that insulated tubing, and then whether or not something that with any kind of insulation, and if it's something that we'd want to look at purchasing for the project.
Okay. What is the maximum working temperature of the rock pipe?
So the rock pipes are pretty cool chemistry. It's actually used for molding for molten metals for mold. I don't really know the right terminology for it, but like to mold liquid metals into solids. So it's good for temperatures above 500 to 600 degrees Celsius. No issue with the current range of technologies that we're looking at on whether or not it's going to be stable at high temperatures. I think we've got the full operating range we're evaluating covered by that.
Okay. Another question about drilling. Any difficulties in drilling 6 kilometers horizontal and intersected wells?
Sorry, what was the last?
And difficulties in drilling that long horizontal wells?
Yeah, I mean, I think it's going to be, it's a complex drilling program, but with the right planning and the right technologies paired together, I think we can execute on it. There's going to be challenges because you're looking at high temp, you're looking at several different technologies that are being partnered together now to complete the full system, but we're putting a lot of work in with the technology providers that would support that drilling program to make sure that we're thinking about everything and planning it all accordingly.
Yeah. Have you drilled more than one Eavor-Loop well at this point?
So we've drilled the only wells that we've drilled at this point are Rocky Mountain House, that demonstration project.
Okay. So how is the cost per megawatt compared to the more traditional power generation? Have you an estimate of that?
Yeah, so it's significantly higher right now. We've kind of proven that we can produce expensive electricity. And that's the whole, I'd say 2022 focus is now going and scaling to a commercial size of Eavor-Loop so that you can show what those costs are going to look like and how the costs can improve over time, because a lot of how we see those cost improvements will be related to economies of scale. And then, you know, as you're drilling for 8 months straight in the same geology, those learnings that you can integrate in and continue to improve on your drilling performance. So I'd say our target is to be competitive with North America grid pricing, like LCOEs of $50 to $60 in a few years, but right now we're at a higher point than that, and we need to work our way down the cost curve by executing on these early projects.
Okay, thanks. So what do you see as a larger hurdle to commercialization for the Eavor between the costs, such as reducing the capital cost, operation cost, and the technical capability, improving the energy efficiency?
No, I don't think the energy efficiency is really going to be a big challenge. I think we understand what the output is going to be subsurface. We have a good handle, and we're working, you know, collaboratively with the power plant suppliers to make sure that we understand that on surface. And we've got a really quite a large R&D team that's focusing on different elements of systems, drilling, different ways that we can increase the efficiency of each installation or drive the cost down. So I think the biggest hurdle is going to be having the money to do these first commercialization projects. That's basically the next step of what we need to be doing. And so that's truly, you know, it's the startup kind of valley of death, they call it, where you've proven the technology, you've done everything kind of on the pilot scale. Now you need the next step of funding to be able to go and prove at a commercial scale that the solution works and it makes sense, and you've got line of sight to the cost coming down. We have a lot of different pieces that can all kind of add together and complement to bring the cost down. So I think it's the step of getting the commercialization first, early projects in the ground.
Okay, thanks. We have just one last question.
Okay.
When and where do you think your first Canadian heat and or electrical project will happen?
Ooh, that's a really good question. I don't even know if I see, like, we're a small company, but everybody's kind of going a million miles an hour. So we do have a team that's probably way more up to speed with the Canadian efforts. I think, yeah, I don't know. I don't want to answer that just because I'm not sure exactly. So I don't want to give a wrong answer, not a wrong answer, just something that's not accurate, you know?
Okay, thanks.
Sorry.
Yeah, there's still a lot of more questions left, but unfortunately we ran out of time, and we will let the folks know, and we will wrap up today's webinar. And thanks, Bailey, for your kind offer to our talk series, and thanks everyone to join us, and good luck to your project in Germany, in Canada. Hope everything's great, and thank you everyone to join, and we will see you next time. Thank you.
Perfect. Thank you.
Yeah.